Hello everyone, thank you for joining us today in the 33rd International Microelectronics Conference by IEEE hosted by the GUC. My name is Mohamed El-Barbary and I'm a senior undergraduate computer engineering student at the British University in Egypt. Today, I will be presenting our paper titled Validation of Driver Drowsiness Detection based on Humantenna effect using facial features. To begin with, I would like to introduce the members involved in this research. The members are myself, Engineer George Sharif Maximus, Engineer Shahab Tariq, and Dr. Hani Bastauros. This presentation is structured as follows: an introductory section where the topic will be briefly discussed, a section where the most commonly used parameters for driver drowsiness detection are discussed, a section that discusses some of the currently used systems, a section for the operational principle and system design, another section for experimental results, and finally, a conclusion that sums up everything. Did you know that car accidents and vehicle-related crashes are actually the reason for the death of almost 1.35 million persons per year? Additionally, they are one of the major factors that affect our economy negatively. That can be seen with how it is projected that by the year 2030, we can expect to see a loss of almost $1.797 trillion. Can you believe that? This explains why automotive safety research and development is a really important field. But why driver drowsiness specifically? To answer that, we can go back to the surveys conducted by the European e-Survey of Road Users' Attitude that reports that almost 36% of motorway accidents are caused by drowsy drivers, which highlights how dangerous this specific type of driving pattern can be. Next up, we have the parameters used for driver drowsiness detection. These parameters are typically divided into three distinct categories, which we will go over in their respective order in a second. First off, we have the physiological metrics. Physiological parameters are defined as the metrics obtained through biological monitoring of the state of the driver's body. These metrics include, but are not limited to, heart rate metrics such as HRV, also known as heart rate variability, which is the measure of the change in heart rate over a given interval, and ECG, which is short for electrocardiogram, where heart rate signals can be obtained and then processed just like any other signal in the frequency domain. We also have brain metrics such as EEG, the electroencephalogram, which when processed just like the ECG can give us insight into the sleepiness and/or drowsiness of a driver through their parasympathetic and sympathetic responses. We also have GSR, which is short for galvanic skin response, which is the measure of electrodermal activity in the human body. Secondly, we have artificial intelligence and computer vision-based metrics, such as facial feature extraction through the usage of convolutional neural networks, eye metrics such as blinking frequency and eye aspect ratio measurement, and lane detection metrics such as off-lane deviation. Thirdly, we have sensors and microelectronic-based metrics, and these include grip strength measurements through embedded load cells or force sensors, measuring the car's deviation using the yaw angle and acceleration, steering wheel metrics such as using gyroscopes, or the steering speed and frequency. And now, we have some of the currently used driving drowsiness systems that are commercially available. We have Valeo's built-in camera system that monitors the driver's fatigue and distraction levels, Mercedes' attention assist system that detects drowsiness through erratic steering wheel movements, and Volvo's comparison system that checks whether the driver is complying with road signs or not as its measure for driving ability impairment. So, what are the components of our system and how does it work? Well, subsection A and B will answer this question. The Humantenna touch sensing technique works on the basis of detecting the induced voltages due to the extremely low frequency electric and magnetic fields on the human skin as a touch sensing trigger. The extremely low frequency electric and magnetic fields due to the 50 Hz frequency of AC power lines can be used in computed through a quasi-static approximation. Additionally, the magnetic permeability of the human body is kind of similar to the free space, which is why we can neglect the effects of the magnetic fields on the human body when considering indoor applications, which makes AC power line electric fields our main source of induced voltage. Secondly, we have the eye aspect ratio measurement, which is a two-step process that consists of 1. Facial landmarking, where we define 64 pairs of XY coordinates to act as the face being modeled for facial feature extraction, such as in figure 12, and 2. EAR calculation, where we extract 6 pairs of coordinates for each eye that represent the borders of our eyes for calculation of the aspect ratio, such as in figure 13. The final subsection showcases the preliminary visualization and proposed system. The system should consist of the Humantenna touch sensor technique integrated into the steering wheel, in addition to the camera connected to the facial feature extraction algorithm, which would help us avoid false positive alarm cases. Now we discuss our experimental results. Our superposed graphs in figure 15 consist of approximately 14 minutes of real-time data extracted from our setup. The graph on top represents the Humantenna effect, where if our voltage is over 5 volts, then our driver is not gripping the steering wheel, and if it's in the region in the middle, then the driver has a normal to weak grip, while having a measurement of 1 volt or less means that they have a strong grip on the steering wheel. Furthermore, for our EAR measurements, the green threshold ratio is 0.26, which means that your eyes are open, and the red critical threshold 0.18 represents your eyes being closed or not detected. Figure 16 shows the test run in which we extracted our data, and also it's the view of the system and the setup. While figure 17 shows a picture of the EAR facial feature extraction algorithm being run on Engineer Shahab during the test run. Finally, as a conclusion, the importance of automotive safety has been highlighted, the danger of driver drowsiness was discussed, multiple research solutions have been discussed for driver drowsiness detection, different market solutions have been implemented and commercialized, our Humantenna sensor has been explained, the eye aspect ratio method for facial feature extraction was showcased, and our results have shown that driver drowsiness is definitely possible to detect through the usage of the Humantenna EAR system. As for future work, we theorize that there is a lot of room for improvement in terms of our Humantenna sensor, and we're currently working on that. Please look forward to our future publications regarding the Humantenna sensor. Any questions? Special thanks to the academic organizers and sponsors for hosting this conference. Thank you for tuning in, and enjoy your day.